So we're just going to introduce the idea of analysing these beams here with this simple example, and we're going to keep everything consumed. So here we have a simply supported beam with a load P, total length L, and P is applied right in the middle, L over 2 from each end. So nice and symmetrical. So first thing we've got to do is determine our reaction forces at A and B. That's always going to be our first step, and this is easy enough because it's symmetrical, so RA and RB both add up to P and they're going to be equal, so they're each P over 2. Yeah. Now, when we analyse these beams, we are interested in knowing when the internal forces are going to change. Yeah. So so anytime our load changes, like we have this force here at RA, and then we have a force here at P, right? So we've got a change in the load between A and D. So we're going to cut a point somewhere in between those. Now this point C is kind of arbitrarily chosen here. It could be here. It could be here, basically anywhere between A and D, okay? And we should get the same result. And then on the other side, between P and then the reaction at B, we're going to also want to look at what the internal forces are through there. So we're also going to cut a section at E, which again could be anywhere between D and B. So if we look at C first of all, the way this is drawn here, we've kind of, hopefully you can see what's going on here. It's a little messy. But we're looking at, first of all, this section from A to C. This is the part here, and we'll take a look at that if we just kind of put a box around that and kind of look at what's going on here. In this example, they've also drawn the other side, but we're not interested in this for now. We'll just look at what's going on in this part that I circled. So we've got a length X. X is variable, as I said, it could be anywhere between A and D. Yeah, so X can vary from 0 at point A all the way up to L over 2 when we reach point D over here. So we've got this applied force RA, which we know is P over 2, and then we're going to have some kind of internal shear V and some kind of internal moment M. Well, what we're going to do is we're going to look at sum of forces in Y, which has to be in equilibrium. So that basically we can see if we take our positive direction as vertical, then we're going to have RA minus V equals 0, and therefore V, our shear force, is going to be equal to RA. Yeah, there's no other force applied. And for our moment, we're going to say we'll take the sum of moments about C, which is this surface here, their cut section. So V is not going to count. We've basically just got, if counterclockwise is positive, well, we've got the moment M applied at C, so that's going to be M. And then coming in the other direction, RA is going to rotate this around this way. Excuse me. We'll have RA, negative RA, should I say. Excuse me. And the distance of that is going to be X. Yeah, this distance X. And that's going to be equal to 0, and therefore M is equal to RA times X. Yeah? Okay, so those would be our expressions for the bending moment, and this expression is valid anywhere between A and D. So this whole section here. And then this would be valid anywhere between A and D also for our shear force. So our shear force is going to be constant, we can see, and our moment is going to vary with X. Okay, so let me just clean up the slide a little bit before we move on. Okay, so the next thing we're going to take a look at is if we then look at this cut through section E. So we've got the same thing. Now we're looking at, if we look at this section of the beam here, again, they've kind of cut both sides out, but we'll just ignore this part for now. Because you can look at either side, you're going to get the same result, the same expression. This time when we do our sum of forces in Y, we're going to have RA minus P minus V to get our expression for V. And then for our bending moment, we have to include this force times the distance X. So again, X is variable, right? So this time X is going to be between L over 2, which is the point D, all the way up to L, which is the total length. So X is going to kind of vary within those limits for this part. So yeah, for our bending moment, we'll have these distances. And then what we're going to have now is we have expressions for the shear force and the bending moment at any point through the beam. Yeah, so now what we can do is, and what we will do, is we're going to go ahead and graph those out. So we found that the shear force between A and D was going to be equal to RA, which is P over 2. So, and it's not going to change, it doesn't depend on X, so it's constant. And then once we get to the other side of P, if we were to take sum of forces in Y here, we would find we've got RA, which is P over 2 minus P. So half P minus whole P is going to give us minus half P. So, and then that's not going to vary again between D and B. So now we've got minus half P, right there. So that's what our shear force diagram would look like. And X is our variable, and when we go all the way from 0 up to L would be the length along the length of our beam. So that's what we're looking at. We're looking at how that varies. Now for our bending moment, as we said, bending moment is going to depend on X, so it's going to vary linearly in X, and will increase to a certain point and then decrease back towards the end of our beam there. So you can go ahead and verify this if you want to. Just pause the video, take a moment to kind of run through, calculate what your expression would be for bending moment and shear, and make sure that your graphs come out looking like these before you move on to the next video, in which I'll go into a more detailed example.